Google aspires to create technologies that solve important problems, and we are relying on machine learning to help us reach our goal. We believe these technologies can promote innovation and further our mission to organize the world's information and make it universally accessible and useful. In order to implement these algorithms and these advanced technologies, for many years we have been relying on Moore's law to give us the computing power that we need. But as you know, Moore's law is in decline, and we cannot hope to get large speedups from Intels of the world anymore. That's why at Google, several years ago, we started to work on a project, and we made a custom hardware for machine learning called Tensor Processing Unit, or TPUs. We have been using TPUs in our data center for several years and found them to give us an order of magnitude better optimized performance per watt for machine learning. This is roughly equivalent to fast-forwarding technology about 7 years into the future, or 3 generations of Moore's law. Let's see what are the challenges that we are facing while making TPUs. The first fact is that our product cycle is short, and time to market is very important for us. Our first CPU was in AlphaGo, which was used in the Go contest in 2016 and was able to beat the top master Lee Sedol. Since then, we have made several generations of TPUs. TPU version 1, 2, 3, Edge TPU, Cloud TPU, and we have more generations to come. So as you can see, we execute very fast, and we need EDA tools that can cope with our schedule. Another fact is that TPU is a complex design and has many blocks running with different clock frequencies and having different power and performance requirements. We also use advanced technologies to make our chip, and for that, we need a high level of collaboration and co-optimization between designer, process, and tool developers. Let's look at this chart from Wilson Research. According to this research, the main type of flaws contributing to respins are functional bugs and clocking issues. And for clocking, CDC verification is very important. For both of the categories, static sign-off and static verification is very important and helps a lot. But the issue is that in the ASIC design community, static sign-off is usually the last stage, and there is no time to ensure quality and robustness. How to address this issue? As engineers, sometimes we need to go to therapy, and if you don't need to, you should be proud of yourself. But if you do, there is a common sentence that they always give you. If it's your job to eat a frog, it's best to eat it first thing in the morning. And if it's your job to eat 2 frogs, it's best to eat the biggest one first. So at Google, we try to listen to this advice. We know static sign-off is very challenging and very time-consuming, so we start as early as possible from day 1 of RTL design. This slide shows a big picture of different static verification checks that we run on our code. Before we submit our code, we have pre-submit, in which we run some basic checks on our code. Then we have linting, in which we have standard rules as well as some custom rules that we have developed internally. Elaboration is to make sure that RTL does not have any ELAB issue. We use a combination of static and dynamic approaches for CDC verification, and we also run RDC. Now, please note that all these tasks are in parallel and are independent of our functional verification. Sometimes we run them even before we do functional verification. Another key advantage here is that this process is early and continuous, which means that any changes in RTL will kick off the whole procedure, and the whole procedure will be triggered, and we run all the tasks in parallel again. Let's talk about the impact of this early and continuous process. I'll talk about CDC as one of the main challenges in the static sign-off. CDC verification used to be last thing in our design cycle, and I believe many companies are in the same boat. I remember in one of our projects, everything was done except CDC. We started to run CDC verification, and the tool was reporting over 50,000 violations in one of our complex designs. Of course, many of these are just false failures, noises, missing constraints, But good luck reviewing 50,000 violations and make sure design is CDC safe. As you can imagine, that's not feasible. That's why we decided to change our strategy and eat our biggest frog first. Now we have a nighty regression in which we run statics tools on all the blocks every night from day one of RTL design. The results are parsed and our dashboard gets updated. Our continuous process will even file a bug and send an email to the corresponding designer if a block is failing. We keep the dashboard clean throughout the project lifetime, and as you can see, it's not easy for the bugs to slip past our methodology and find their way into later stages of RTL design. This continuous process is reducing the noise level as one of the most pressing challenges in RTL sign-off, and the result is a significant reduction of later stage RTL changes and cutting at least a month of chip development time compared to our previous methodology. In terms of what we must have, we are looking into the future and thinking about possible approaches that can help us develop our next generation complex chips. And we are collaborating with EDA vendors, including the static tools, to make it happen. One is EDA on the cloud. So we are facing about over 100 billion in investment in cloud infrastructure every year. And at Google, we have this unique advantage because we own vast computing resources on the cloud, as well as fast networking and lots of storage on cloud. So why not just use them for EDA flows and move our EDA flow to the cloud? And by that, we can get scalability, elasticity, reliability, and security, and all of them are very important for us. Another trend is based on the fact that we are at a unique advantage at Google due to our massive scale detailed logs and because Google is the first AI company. The idea is that in the past decade, hardware and system have significantly transformed machine learning. Now it's time for machine learning to transform the system. 70% of the design cycle involves human in the loop. And by using machine learning, we believe we can reduce that and have faster design cycles and cheaper chips. Thank you very much. I will be happy to take any question at the end. And by the way, we have openings in our team, and we need more bright people to do all this cool stuff. So please come and join us. Thank you.
From your experience, why would you use multi-mode CDC over single-mode CDC?
Yeah, it's a good question. Actually, in our design, we use a lot of clock muxes, by which we want to choose different clocks based, and we have different modes of operation, and based on that, we can choose which clock to use for that IP. And sometimes we also make our IP very general so that we can use it for different purposes. And again, maybe for different chips, we need different clock frequencies. For all of these, we need to have support for clock muxes. And that's why we need to have multi-mode support so that we don't want to repeat the same strategy for different modes. And that's the nice thing about Verix CDC, and we decided to switch to that because it can do it in one shot. Otherwise, you have to do run CDC, Meridian CDC, with every mode and review that.